In this question it is given that let z bar denote the complex conjugate of the complex number z and let I is equal to under root minus 1. Then in the set of complex numbers, the number of distinct roots of the equation this. To solve it, it is clear that this can be written as z bar minus z square equal to iz bar plus iz square. That is, I get 1 plus I into z square equal to 1 minus I into z bar. To proceed further, I would like to divide by z bar. But we know that we are allowed to divide by some variable only when it is known to us that that variable is non-zero. But because z bar can be 0 also, therefore we will be proceeding further with two possibilities. Either z bar is 0 or z bar is non-zero. If z bar is 0, then z will also be 0, and in this case this equality will be satisfied. Hence one possible root of this becomes z equal to 0, and afterwards if z bar is non-zero, then I get z square upon z bar equal to 1 minus I upon 1 plus I, and clearly this is equal to minus I. And after this, there are so many ways of proceeding. One way of proceeding further is, if you are somehow able to find the modulus of z also and argument of z also, then you will be getting the value of z. And finding the value of modulus of z is not difficult. If I take modulus on both sides, then I will be getting mod z square upon mod of z bar equal to 1. That is mod z square upon mod z equal to 1, which means mod z equal to 1. And once mod z is known to us, we can proceed further by multiplying and dividing the numerator denominator by z. We will be getting z cube on mod z square equal to minus I. That is z cube equal to minus I. That is z equal to minus I to the power 1 by 3. Clearly we will be getting three different values of z from here. There are so many ways of calculating it. The best is using the concept of de Moivre theorem. You can easily get the three values of z. But I don't require the values of z. I just want to find the number of roots. That is, I'll be getting three roots from here, and one root I have already got, that is z equal to 0. Hence I can say number of distinct roots of this equation is 4. Another way of proceeding further, which I don't like, just as an alternative I'm telling you, otherwise the previous way was much better. The alternative way of proceeding further will be, let z equal to x plus iy, and you will be getting x square minus y square plus 2xyi equal to minus I into, putting the value of z as this and simplifying z square upon z bar equal to minus I will be reaching here. And equating real part and imaginary part, x square minus y square equal to minus y, and 2xy equal to minus x. I start from here. Note that there is a AND word between these two. This implies that 2xy plus x equal to 0, that is x equal to 0 or y equal to minus 1 by 2. And we will be taking two cases, either x is 0 or this. If I take x equal to 0, then from here I will be getting y square equal to y, that is y square minus y equal to 0, that is y equal to 0 or 1. That is when x is 0, in that case y can be 0 or 1. But when x is equal to 0, y equal to 0, this case will be rejected, because when I started from this portion, I had supposed that z bar is non-zero. Z bar is non-zero means z is non-zero. The case z equal to 0 is separate, that I have already counted. The case z equal to 0 will not be counted here. Hence, I have got the conclusion that x equal to 0 and y equal to 1. And if y equal to minus 1 by 2, from here I can get the value of x. Note that there was AND between these two. And putting the value of y equal to minus 1 by 2 here, I will be getting x square minus 1 by 4 equal to 1 by 2, putting y equal to minus 1 by 2 here. That is the value of x will be plus minus root 3 by 2. That is, two more possible solutions we have got are x equal to root 3 by 2, y equal to minus 1 by 2, and next possible is x equal to minus root 3 by 2 and y equal to minus 1 by 2. Hence, in total we have got four solutions: this, 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 and one solution which was z equal to 0 we have already found. Hence, in total I can say there are four solutions. And one more possible solution is, let z equal to r e to power I theta. From here I get r square e to power 2i theta upon r e to power minus I theta equal to minus I. That is, I get r e to power 3i theta equal to minus I. And keeping this concept in mind that mod of e to power I alpha is always 1, by taking modulus on both sides I can say r is equal to 1. And once r is found to be 1, this equation becomes e to power 3i theta equal to minus I. Note that whenever we suppose z equal to r e to power I theta, theta always lie between minus pi and pi. For other values of theta, I will not get different value of z. I will be getting different values of z only when theta lies between minus pi and pi. It is not necessary to take minus pi to pi. We can also take 0 to 2 pi, and more possibilities are also there. But because we are comfortable with dealing with the questions of principal argument of z, therefore it is better to use this. And therefore now I get cos e theta plus I sin 3 theta equal to minus I. That is, cos 3 theta equal to 0 and sin 3 theta equal to minus 1. From here I can easily say that because if sine theta is minus 1, cos theta will automatically become 0. But note that after this we can't proceed by taking this and rejecting this. In the present case I have taken this and rejected this because once this is true, this is automatically true. But if I take this and reject this, this will be wrong, because if cos theta is 0, in that case sin theta can be 1 also and minus 1 also. That is, you will be getting extra values also if I take this and reject this. But if I take this and reject this, I will not be getting any value of theta which doesn't satisfy both. But the value of theta which will satisfy this will surely satisfy this. And this implies that theta equal to 2n pi minus power 2. You must be knowing that equal to 1 means 2n pi plus power 2, equal to minus 1 means 2n pi minus power 2. This is direct, you must be knowing. If you don't know, remember it. Theta equal to 2n pi by 3 minus pi by 6. And putting the values of n, where n is any integer. One case, if I take n equal to 0, I get the answer minus pi by 6. If I take n equal to 1, then I get the answer pi by 2. N equal to will give the answer beyond pi. N equal to minus 1 will give the answer minus 5 pi by 6. Hence we have got three values of z, that is z equal to 1 into cos minus 5 pi by 6 plus I sin minus 5 pi by 6. Second, 1 cos minus pi by 6 plus I sin minus pi by 6. And z equal to 1 cos pi by 2 minus plus I sin pi by 2. That is three values here, and one value we have already found, that is z equal to 0. In this way we have got four solutions.